JBBRXG11 or Jibber group. Our project is to extend XNA to provide DirectX 11 functionality. The first video showed tessellation and a geometry shader. This video shows our first experiment with a compute shader. It's not actually a very useful example. It simply adds together two vectors, and the way it's invoked means that it adds the same vectors 60 times a second. But the thing that we're pleased with is that we've got all the buffer structures and the declarations and all the bits and pieces of infrastructure required to get a compute shader in operation. Let's have a look first of all at the compute shader code itself. This is based on Microsoft's basic Compute 11 example. We had to decide which of the different kinds of buffers that compute shaders will bind to experiment with first, and we decided on the structured buffer. So a structured buffer is just an array of structs in effect. The struct we're using is defined up here, and it only contains a single float. Back on the CPU, in fact, although we declared a buffer structure, we don't really make much use of it. It was possible to pump data in and out from an array of floats, and that's mostly what we did. On the shader code here, we declare two structured buffers, A and B. Those are the vectors that are going to be added together. And we declare a read-write structured buffer, C, which will be accessed via an unordered access view. The main function of the compute shader is here. It's called CS_main. It's set up to run 16 threads at a time, and it simply adds one element of A to B and puts the result in C. To get the compute shader put in place on the GPU, we use the normal style of shader assignment that's typical to most XNA programs. We just have a pass which sets the compute shader. So we activate this technique, initialize the pass, it puts the compute shader in place, and then it runs. Let's have a look at the XNA program that invokes this. Typical sort of XNA syntax. We've declared at the top here the cbuff struct that represents a single item in the structured buffer. Again, it's just a single float, and we barely refer to this, so I won't say any more about it. The compute shader itself is simply an effect. It's picked up and loaded like any other effect in XNA. For buffers, we have buffers both on the CPU in this program and on the GPU. CPU buffers are just arrays of float, two to contain the vectors being added and one that will pick up the result into. The buffers on the GPU are a bit more interesting. So there's three declared here: A buff, B buff, and C buff. The class compute buffer is new. I think after some experience with this, we can probably fold it back into the vertex buffer class. But for ease of development, in effect, we've made a copy of the vertex buffer class, changed a few things, and we've called it compute buffer. It's capable of allocating GPU structured buffers and setting up either the read view or the unordered access view as required. We'll see how that's declared in a moment. Just rolling down here a bit, in fact we'll see how it's declared now. Let's have a look at the load content routine. The compute shader effect is just loaded in completely the ordinary way for loading an effect in XNA. The buffers on the CPU are loaded and initialized. A ends up with values 0, 2, 4, 6, etc. B ends up with values 0, 1, 2, and C is not initialized. So those are ordinary arrays. We've had to extend the syntax of XNA a little bit to allocate buffers, the compute buffers appropriate for binding to the compute shader. So the constructor for compute buffer takes a graphics device. It takes the buffer structure which inside this routine really only leads to a bit of analysis that figures out how big one element is. We pass the number of entries we want, 1024 in this case. Normal compute buffer usage, none just means that the CPU won't be trying to access this buffer at all, aside from the initialization. In the same way as we set data on a vertex buffer, the compute buffer has a set data routine. Should strictly, I suppose, pass an array of cbuf structures. In fact, we just pass an array of floats because it's only the size of the data that matters. So, allocated a structured buffer on the GPU, filled it up. For B, allocate another structured buffer and fill it. For C, we need an unordered access view. We've arranged to ask for this by having a new value of the compute buffer usage enumeration, just unordered access, and that will mean that cbuf is accessed via an unordered access view. It also means that we can't call it set data routine because it's not available for CPU write access. Load the font. We roll down to the end here. Let's just have a look at the draw routine. So there's a call on sprite patch to draw a string at the top. I'll say a little bit more about it in a moment. The more interesting part, to do with the compute shader, we simply have extended the parameter set value routine to deal with compute buffers. And inside that set value, it knows whether the compute buffer should be accessed with an unordered access view or with an ordinary access. So we have perfectly ordinary XNA parameter setting for the external variables of the shader, A, B, and C, and we just bind those up to the three buffers that we created on the GPU. Remember, Jibber still uses the old XNA 3.1 syntax. We will get around to changing that. So the process of invoking a shader has this slightly awkward begin, iterate through the passes, begin the pass. The new thing that we've added here is a dispatch routine to graphics device, which actually runs a compute shader. And in this case, we're running buffer size upon 16 copies because we get 16 threads on the on each invocation, however that works. To get the data back, we just have a cbuf.getData routine here, which fills up the array C. And at the end, I just display some stuff on the screen. Display the first few values of each vector and the first few values of the result. Let's run this and see what that looks like. That's the result. It is actually calling the shader 60 times a second. We can see the input vectors and we can see the output vector, which is the result. So it works. One last thing to explain. We have a check in our graphics device implementation that a vertex declaration has been properly set up before we invoke a shader. Of course, the compute shader doesn't require a vertex declaration, but that check hasn't been removed for our code yet, from our code. So if I just invoke a graphics operation before the compute shader starts, that means that that check is satisfied. Further actions required. So there you have it. A compute shader running under XNA. Thank you for watching.